Hello and welcome again to my physics online video lecture series. Today's video we're going to be doing a little bit more discussion about Kirchoff's rules. And specifically I want to discuss sort of my process for solving complex circuits using this Kirchoff's rules. Everybody has a process that they've developed for themselves, and there's a different variety of ways that these get explained, both by physics and by engineering, especially electrical engineering textbooks. There's a variety of different sign conventions that get used that are self-consistent, and those will work out. I'm going to stick with the sign convention that I use, which I discussed in a previous video. Essentially, I follow the E field. So if I'm going around a loop in the same direction as the current, then I call that a positive current. That means that if I am going from minus terminal to plus terminal inside of a battery, then that is essentially a negative EMF. And how I label my loops is a little bit different than how other people do. But I'm going to show this process. It works. And if you're following along with a textbook, it may have one of a variety of other processes. So let's get into that. I have here a circuit diagram that I just kind of drew up on this site called circuitlab.com. Now, they are not sponsors of this video or of any of my courses or anything. They're just a resource that you can use, although it's free. But you have a free trial for like a few minutes, and then you have to sort of create an account. But you can always clear the cookies if you want. One thing to know about Circuit Labs, when I drew this circuit up, it has voltage sources labeled like this, and then it just has resistors. And so typically we label internal resistances for a battery with a lowercase r, and typically your battery would be labeled like this in a circuit diagram. So there is sort of a difference between this diagram and the type that you encounter in a lot of textbooks and the type that I usually label. Now, beyond that, let's note that what I'm doing in this video is not trying to necessarily solve for the final answer of the current. I'm just trying to give the basic process, because solving this whole thing may take longer than the video limits that I impose on myself. Okay, so that caveat aside, what's the process that I usually use? Well, the first step is that I draw or redraw my diagram. So in some sense, this is like my redrawn diagram. And then I label around the diagram's nodes and corners and so on. And I labeled it like A, B, C, etc. So I'm going to just pick a point to start from. That point I'm going to label as point A. And then I'm just going to kind of go around the diagram. So here's A, B, C. Down here I'll label as D. This node right here is E. And this point right here before the battery is F. What that will allow me to do, and the reason why I label it this way, is it allows me to more easily just define my loop based on what letters I'm going to for the loop. So some people would say, no, just label each loop, and so like this loop right here would be labeled as something like loop 1, and then this loop right here might be loop number 2, and the outer loop might be labeled number 3, etc. I label the corners and then describe what I'm doing. Okay, so that is our first step. The second step is, if the circuit is not pre-labeled with currents, then you need to kind of define what the currents are. for your circuit. And largely this is a matter of defining currents going into and coming out of junctions. So I'm going to kind of start at point A and say that this current right here, I'm going to call current I1. And then I'm going to bring current I2 out of the junction and current I3 out of the junction. And so I basically labeled going in and coming out. I can then kind of extend where this current is going by just following around until I get to the next junction. So all of this is current I2. This one right here, I3, just continues down here to this junction. And then I1 kind of continues, or we can extend its origin around until we get to a junction. So all of this is I1. So now one thing to note is that I've labeled these directions without having any idea necessarily what direction each current will be in. But that's okay, because I will apply my rules, I'll apply my sign conventions, and the unknowns are basically the currents. If I solve through the system and I get 3 positive numbers for I1, I2, and I3, then it means I've set all the currents up in the direction that they actually flow in. If I go through and solve and get, let's say, like I1 is positive, I2 positive, but I3 negative, then that means that I3, rather than flowing down this branch, actually flows up the branch. So you could say that in some sense, if the current points the wrong way, it'll end with a negative value. Similarly, if it points in the right way, it'll end with a positive value. This is true, by the way, even if what ends up happening is you're given the currents, then it means that you may be told like these are all positives, and what will happen is that when you go to solve your system, something will end up negative. And so that kind of tells you that one or more of the currents is backwards. It's a little more complex, of course, if you're told these are the current values and you've labeled them to figure out which one is actually wrong. But by and large, you can go through and solve and find that, yeah, one of these currents was labeled incorrectly. And so that just is sort of a double check for you. Step 3, once you've labeled all this, is to apply the junction rule at one or both junctions. And so, for example, at junction B, which I'm just going to circle with a B in it, I have I1 going in, so I would have I1, and then coming out I have I2 and I3. Generally speaking, your junction rule just is that the sum of currents going into the junction is equal to the sum of currents coming out of the junction. You can likewise go to junction E, and going in, I have I2 plus I3. Coming out, I have I1. Now the thing is, I already have this equation. It's just kind of mirrored from equation B. So I'm just going to draw a little line through it. It's not that the equation's incorrect, it's that it's not giving me any new information. So important point here. You need linearly independent equations to solve your system. So if I have n variables that are unknown, then I will need n linearly independent equations. In this thing's case, my unknowns, by the way, are my 3 currents. And so I have 3 unknowns, therefore I'm going to need 3 linearly independent equations. I will be able to generate more than 3 equations. In fact, I think for this system I have 5 equations that I could generate. Okay, step 4 is to use the loop rule and Ohm's law to generate the additional equations. So as a little reminder, your loop rule basically says sum of voltage drops around a closed loop is equal to 0. And then, of course, Ohm's law says that delta V is IR. Now, your delta V's in here could be IRs for resistors. It could be EMFs for a battery. If you have a capacitor, then you can use Q over C, etc. I've just used Ohm's law as shorthand for what are we putting in for our delta V's. Now, most engineers would say at this point that what you're doing is you're picking a point in your loop to call the ground and just moving around until you return to ground, and that's fine. That does work. It also just works to say I'm going around a closed loop, starting from, let's say, A and going A, B, E, F, A. So in some sense for the engineers, A is sort of what I've chosen as my ground in that loop. So let's set up some equations for these loops. Okay, my first loop, like I said, might be loop A, B, E, F, A. So I'm starting here. I'm going through the first resistor. That is I1, R1. And then since I'm going in this direction around that loop, it's the same direction as the current. This term is positive. Then I'm going this way through the next set of resistors, and this way through the next resistor, and so on. So that means that my current actually for this loop is positive for all terms. This one is I3, R3. The next one is I3, R6. And then I1, R5. And then I go through the battery. I'm going from minus terminal to plus terminal. So that means it's actually minus the battery's EMF. And then plus I1, R1. Whoops, the first one, sorry, I said I1, R1. I meant I1, R2. So this is I1, R1. Okay, now we do the same thing for the other loops. So I have a loop B, C, D, E, B. And that one I go through I2 first. So I have I2, R4. Sorry, I go through R4 first. Then I have R8. So plus I2, R8. Going from plus to minus terminal inside of this battery. So this is EMF number 2. I'm going through R7 in the same direction as current I2. I'm going from plus to minus in the next battery, so that's plus EMF 3. And now I'm actually kind of going counter current through R6 and through R3. So I actually have to subtract I3, R6, and I have to subtract I3, R3, and all of that equals 0. I can do it now for the last loop, A, B, C, D, E, F, A. I'm just going to write out what the answer is, but you should pause it and try to get what your loop is before watching further. So all of this is what I've come up with for that loop. Now our next step is to again identify that we needed 3 equations, and right now we have 4 if you count the one that I crossed off earlier. Turns out that this last equation is not linearly independent either, so I remove it. And I also forgot that the top equation I needed to write an equals 0 on it. At this point, I have a system of 3 equations and 3 unknowns, so let's write those out. My system of equations is, first I1 is I2 plus I3, then my equation from loop ABEFA, and then actually the next one is from BCDEB. From here it's basically an algebra problem. I have a system of 3 equations and 3 unknowns, so I solve for the unknowns. It helps to convert all the units into MKS, and put the numbers in and suppress units. That means ohms, volts, and amps. So in other words, I've converted all of my resistors into ohms if necessary. Sometimes they're in kilo ohms or something like that. In this case, they all were already in ohms and in volts. But if they were in like kilovolts or kilo ohms or something like that, I'd need to convert those units to ohms, to volts, to farads, to amps, that kind of thing. And then all my known values, I just plug into these three equations here, here, and here. And so I've rewritten them with the known values plugged in. And so it's easy to identify now that, yeah, the only three unknowns in here that we don't have values for are I1, I2, and I3. So this is kind of like solving an equation where you have like x equals y plus z, 150x plus 100z plus another 100z plus 400x minus 9 plus 10x is 0. 200y plus 15y plus 12 plus 12y plus 7 minus 100z minus 100z equals 0. So you have x, y, z, you solve. And all of you who are taking this class should know at least a couple ways of solving a system of equations. There are quite a few ways. There's an iterative approach, there's a graphing approach, which typically works best if you're in 2 or 3 unknowns. There's the matrix determinants approach, which is great for graphing calculators, that kind of thing. There's solve and sub. So for example, you could substitute equation 1 into equation 2 to get rid of all the I1s, and now you have 2 and 3 would all be in terms of I2 and I3. And you can also do add, like multiply and add to eliminate. I would say that it's a good idea actually to combine your like terms as your next step. So at this point, we would want to combine like terms. And so our equations would now look like this. The top one, once again, doesn't really change from before. But equation 2, I have an I1 term here, and I have an I1 term here, and I have an I1 term here. And then similarly, I have a couple of I3 terms here and here, which I'll double underline. And so that one, I basically got 150 plus 400 plus 10. So that should be 560 I1, and then 100 and 100, so 200 I3 minus 9 is 0. And then in part 3, or equation 3, I could likewise go through and find my I3 terms, which are this term right here and this term right here. And then there aren't any I1 terms, but there are some I2 terms. Let's do this in orange, I guess. So I've got 200 of I2. I've got another 15 here. I've got another 12 here. And then there's also actually just the 2 voltage terms. So if I combine these, 200 plus 15 plus 12 should give me 227 of I2, and then minus 200 of I3, and then plus 12 plus 7, so plus 19 is equal to 0. And this is again kind of just allowed me to kind of clean up my equations a bit so that I just see my 3 unknowns in sort of symbolic form, I1, I2, and I3, and then in non-symbolic form everything else. So now I could go and sort of like solve the system for a final value. So I basically have subbed in equation 1 for equation 2 to get rid of the I1 term that was previously here. And again, combine like terms, this should give me 560 I2 plus 760 I3 minus 9 is 0. And now, you can combine that with equation 3, which is right here, is saying 227 I2 minus 200 I3 plus 19 is 0. So you can essentially take this one maybe and solve it for I2. And so I2 would be 9 minus 760 of I3, all divided by 560. And so now I can substitute that into this equation for the I2s. And so I'd have 227 times 9 minus 760 I3 all over 560 minus 200 I3 plus 19 is equal to 0. And so now basically I would just sort of solve this one for I3. So remember that you can break fractions up to look more like this. So 9 over 560 minus 760 I3 over 560. And so basically you now are doing some calculator work to solve for I3. So the basic process is that you multiply the 227 by 9 over 560, and then you multiply 227 by 760 over 560. You get these numbers. Then you also have to subtract the 200 I3 from this I3. You've got to add the 19 to basically this number over here. And then what you end up getting is 508.071 I3 plus 3 plus 19 is 22. So 22.648 is equal to 0, and therefore negative 508 and change I3 is equal to negative 22.648, etc. And so I3 is this number divided by 508, which gives us 0.04456. So we'll call this 0.0446 amps. And that's actually kind of like the answer to how much current will be passing through this ammeter. And since it's a positive number, it means I've drawn I3 going in the correct direction in my diagram. So to sort of recap what all we've done, for these complex circuits, you start off by drawing or redrawing your diagram. You've got to then label all of your junctions, nodes, resistors, currents, etc. Then you set up your currents for each branch from the junction. You use the junction rule to get some equations that relate currents to each other directly. There aren't any other parameters in those. Then you use the loop rules to set up any additional equations you may need, and these will basically relate currents to voltages to resistances, etc., via Ohm's law, via the definition for capacitance, etc. Once you've done that, you will inevitably have too many equations. In fact, you'll have typically double the number that you need from the loop rules, and there's usually several extras from, double the number you need from the junction rules, and there's usually a bunch of extras from the loop rules as well. And so what you have to do is find a set of 3 or 5 or whatever linearly independent equations. However many variables or unknowns you have, that's how many linearly independent equations you have. So you kind of go through and eliminate some of your equations. And then my recommendation is convert everything into MKS units, so that's volts, amps, ohms, watts, farads, henries, etc. And then you basically plug the numbers into your equation, suppress units. So if you look back here, when I plugged all the numbers in, I don't have 150 ohms times I1, I just have 150 I1 because I'm already in ohms and I know I'm in ohms. I don't have 9 volts here, I just have 9. And so I just keep track of what units I converted everything to, and I know at the end that if I'm solving for a current, then it's going to be in amps. If I'm solving for a resistance, it's going to be in ohms, etc. Then once you've plugged in the numbers and suppressed the units, you basically just want to solve your system of equations for the unknown variables, be it the current, be it an EMF, be it a resistance, or whatever. And if applicable, you can use Ohm's law, the equation for power, whatever, to solve for further factors. So if the question is asking, instead of like how much current is in this ammeter, maybe it asks like what's the power draw of this resistor. So you'd go through, you'd solve for I2, and then you'd go back and use I squared R to get power. Or if you want the voltage drop across, say, like this resistor here, you've got I3, and so you'd multiply it by R to use Ohm's law and get that voltage drop. So that's basically it. That last comment on this page kind of fades behind the video. So here it is again. And then a reminder, at the sign conventions that I use, essentially I'm following the direction of the E field through my circuit. Other people do it differently. Their answers will also work. So as long as you have a consistent set of sign conventions, your answers will work out. So that's it. This video, I ended up going ahead and making it a sort of double length video to work through the entire example instead of just showing the process. And hopefully that helps you, and thanks for watching.